Okay, today we're going to change gears. We've been speaking about stars and stellar evolution. We've covered supernova. I've explained, sort of, how we get the gold out of stars. We discussed supernova, giant black holes, although I didn't tell you how they're made. So we need to talk about another component in the universe, and that is the external galaxies. The galaxies are an interesting study. They were only known about, we understood them 100 years ago. That's pretty recent. We understood something about them 100 years ago, and we're learning more every day. The galaxies are seen clustered. Very often there are more than one galaxy in a region where there's one, there's two, or three. This, of course, these two are stars, but these are galaxies all in the same, more or less the same distance. They're close to each other. A question that arises is, why are they close to each other? Can we understand the distribution of mass represented by the galaxies? And we'll talk about that on Thursday. Okay, so before I do that, I want to just ask a question. All right, black holes. Where are the black holes? Are they the biggest black holes in the center of stars? Are they have mass of 10 solar masses? Or are they the center of galaxies? Just want to check and see if anybody was paying attention when I lectured last time. Get out your cards. There's another question coming, so you got to get out your cards. How many of your lecture classes use cards? The only one. The only one?
Yeah.
Really? Do your other classes have clickers? Or some way you can engage the speaker? You sort of sit there like a lump on a log? No feedback at all? Jeez. Well, I think these techniques of cards or something like this, clickers or whatever, is good for me is to see what you know. It's good for you to wake you up and to ask you to engage your mind a little bit. So these are all based on some careful thought that's been gone into the lecture series. You know, apparently lectures were invented in the Middle Ages, and they were for people who didn't have a book, because books were very rare in those days. Books were precious. And the expert would talk about a subject, and people would write a book or write what they're talking about. But now that we all have books, too many people tend to read the book or sort of read something on Wikipedia and think they know what's going on. And you can, some other courses in astronomy I know get hilarious responses to the questions of they're asking them to do something or fill something out on an exam, and the answers are just crazy. But they got them from Wikipedia, so it must be right. All right. Well, obviously it's three. I'm sorry. Black holes are in the centers of galaxies. They're not found in stars. They're certainly not in the middle of stars. They can momentarily be in the center of a star that is dynamic, that is crashing through, it might form a black hole instantly while the star collapses, but we don't see those. Well, we don't know if that happens or not. Okay, another question. Black holes. How do we measure that these black holes exist? Kepler's third law. We have a special method for measuring the mass, or they can't be measured because they're black. So how do we know that black holes have a mass? Okay, let's take your cards out again. Come on, talk to your neighbor to get an idea if you're not sure, or if everybody's sure. You got cards? You don't have a blue card?
Blue and a white.
I don't have any with me.
Here, I'll
All right. The answer is, of course, number one, red. Black holes are measured because they have a mass. A mass is visible from the black hole. The only thing that's hidden from the black hole is the surface of the object, but it's still curved space to very large, infinite distance, and that curvature of space is what you measure when you measure this, when you use Kepler's laws. Okay, today I want to talk about galaxies. This is our galaxy, sort of, a drawing. The galaxy features bulges. It has bulge in the center that's typically red. A red system means the stars are old. Blue systems on the outside means the stars are young. At least the stars you see are young. So these hot blue stars, they can't live long because they die in about 100 million years, they're dead. So these stars on the outside of the galaxies are blue. Most of the distribution is in a disk of matter and a bulge in the center, which is not confined to 2 dimensions the way the disk is. The disk is typically less than, well, it is 28,000 light years, or about 8 megaparsecs, 8 kiloparsecs, 8,000 kiloparsecs. Kiloparsec is 1,000 parsec, okay? So it's either 28,000 light years or a distance of about 8 kiloparsecs. All right, and we are out here. We're not in the center, we're not on the outside. We're just in a place that's just right. We have heavy elements that are needed for making iron and cobalt and all the magnesium and everything else that makes us up. The galaxy apparently consists of mass like this, and it has a lot of halo stuff in it. The halo stuff is very often the diameter of the disk, radius of the disk, thickness of the disk is 300 parsecs, number of stars, a huge number of stars, probably more stars than McDonald's sold hamburgers, although I'm not sure about that. When I was a kid, these signs used to be up, millions and millions, then finally it was 100 millions, 100 millions. Now they don't have any signs anymore. But, okay. And so there are lots of stars, and there is other things here. In the halo, there are globular clusters. Why are they there? And why? What do they mean? What does this mean? They are seen to be distributed somehow loosely around the center of the galaxy. That's not clear what they are. That is something that is debated still. Okay, now the regions of the Milky Way. The disk contains younger generation of stars. contains the dust, and it has these open clusters of thousands of stars all at once. A lot of the stars whose Hertzsprung-Russell diagrams we put up on various slides were open clusters, so-called. It's a cluster made out of a gas cloud not that long ago, maybe 500 billion years, but they're still together. The stars don't dissipate immediately. Okay, the bulge is a mixture of old and young stars. That's the thing in the middle. And finally, the halo contains older generation stars, contains no gas or dust, and it is where the globular clusters are. So there are three components: disk, bulge, and halo. Now, we have in the formation of stars, we've seen that there are disks that form when stars are formed. We see the stars that are forming now, and they always seem to have a disk. The disk is the place where the planets are formed. The disk is the same idea as the disk of a galaxy. It is for the same reasons that it's there. And what are the reasons that a disk exists in a star-forming region? Anybody know? Why does all the material settle down to a disk right away? Okay, this is not an easy question. The disk forms when the material radiates energy. It has a lot of energy when it's hot, and the energy cools it off. Radiates energy, shining light, and that comes from the energy of that light comes from the thermal motion of the gas material. The gas moves slower after that, and it's confined to a thin disk. Why doesn't it immediately fall into the center of the galaxy or center of the star? Why doesn't that just fall? Why is it all over then? Bang. Everything falls into the star, center of the galaxy. What stops it? Anybody? What stops it is angular momentum. You cannot fall into, when you go into something, you're prevented from getting closer because the angular momentum is carrying you away. Otherwise, it would fall into the center of the star or center of the galaxy or whatever. But angular momentum is what keeps the system from collapsing all the way. So the disk is a region where the gas collapsed down to a plane and later found a way to make stars. That's what we know now. So the planes are naturally a part of galaxy formation. Okay, and our plane, the plane of our galaxy, is very beautifully shown. Let me turn this light off. So you can see this a little better. Okay, this is a picture in the, I don't know. I thought it was a picture from taking the infrared, but I'm not sure. This is a whole sky picture seen from the Earth. Okay. So this is a picture centered on the center of the galaxy. We're not in the picture, of course. This is what we see when you look out all around the sky. Here's the north celestial pole. Here is the North Pole, South Pole. Well, this is in equatorial coordinates. It's been rotated. So this is North Celestial Pole. And this is the plane of the Milky Way. Now, the Milky Way, the center, is obscured by dust and gas in that direction. The dust and gas was unknown. When it was first observed, they didn't realize dust and gas obstructs everything behind it. Here it's obstructing the stars behind it. This is this dust cloud is part of that dust is junk, little specks of dust out in space. That's all it is. It's not very thick. It's pretty rare, but the dust comes there and scatters the radiation trying to move through it. This is okay. So let me see. This is this right here is the Andromeda galaxy, the galaxy closest to us, or the nearest big galaxy. This is the Magellanic Clouds, large Magellanic Clouds, the small Magellanic Clouds. These are seen in the southern sky, and this is seen in the northern sky. How many of you have seen Magellanic Cloud with the telescopes? It's not easy to see it, but it is visible, and it should have pointed at it. Anybody try to point at it? It might be really bad to see it from the Berkeley campus. But this is something you can see. It's not really dramatic when you look at it, though. That's unfortunate. All right, so this is the plane of the Milky Way. And the plane goes all the way around the sky. Here's the anti-center direction, but here's the center. So the plane is all around the sky. Okay, now when people looked at this, they first of all didn't have a whole picture to look at. 100 years ago, they had snapshots. They didn't really have anything like this. They knew about these fuzzy little things in the sky, which are now called galaxies, but they didn't know what they were. They knew they didn't move, and they put them into a catalog so as to distinguish them from comets, which were moving. They didn't want to be classified. They didn't want them classified as comets again and again. Comets were something to look for from ancient astronomers. So they had a list of these nuisance objects. Okay. All right. Now those are simply that's the galaxy. Here is a picture of a globular cluster. Globular clusters contain up to 1 million stars. They're very concentrated in the center, and they're very red. Dating these things in the same way we did before by the age of the main sequence in the Hertzsprung-Russell diagram tells us that these globular clusters are usually older than 10 billion years. They're really very, very old. Okay, that's one. This is a globular in our galaxy, 47 Tucanae. Here's another one. NGC 5139. This is New General Catalog. I think this is compiled in England. It looks blue, but that's just a printing of the print. It's really a red globular cluster. Okay. And here's another one, M15. Okay, so these clusters all look about the same. They're very concentrated, and understanding them is a different subject. We're not really going to talk about them much, but that is the subject of investigation. Okay, so now let's talk about the history of discovery. How was this stuff understood? In 1917, Harlow Shapley, he's observing from the ground. Remember, they're born in this Earth. They don't know anything. He's trying to figure something out. Harlow Shapley notices that the globular clusters are not distributed about the Earth, evenly about the Earth. They're concentrated toward this galactic center region. He didn't know it was a galactic center. He just knew that the globular clusters were concentrated there. Why? He couldn't say why. Okay. So he said, okay, let's assume the globular clusters orbit the center of the Milky Way. Just assume that. And then let's look for variable stars. Look for stars that are blinking at us. We know, he says, look, we've got stars nearby called our Lyrae that blink every day, and we know that they're equivalent to a 50-watt light bulb. Blink, blink, blink. So if you see them and you see how bright the star is, you can tell how far away it is, because I'm assuming that if it's blinking, it's the same star. If it's further away, it'll be fainter. And so he uses these combinations of facts: the blinking rate and the brightness of the star. He assumes the brightness of the star is the same. It just varies according to the blink rate. And on that basis, he was able to estimate the distances. And he got it. He was the first to estimate the distance to the globular clusters of about 28,000 light years. All right? Now, if you start to measure the distance to globulars, you've got to establish a very careful distance ladder. And you have to, the distance ladder astronomers use is something that is elaborately constructed. Let's see if I've got, all right. Now, let's take an idea about the distance ladder. Here we are on the Earth, and we want to know the absolute distance of everything. So what do? Nowadays, you can tell the distance of the solar system because you measure the time it takes for a light pulse. You bounce radar off of Venus, for example. What does that mean? That means you have a set, your radio receiver sends out a pulse, and then it comes back. It hits the surface of Venus and bounces back. How long does it take to bounce back is something you can time very accurately. Since you know the speed of light, you can immediately determine the distance to Venus. So that's one thing you can do. And people have done that, and they get a very accurate distance to Venus. There's no question about it. We know about the parallax method. We've used that. Parallax can measure the distance to nearby stars. Goes out to 100 light years. This is a very small fraction of light years, 10 to the minus fourth. This is 100 times larger. And then you can do main sequence fitting. For example, this is a key that you can use in the galaxy. You have here, you have luminosity. Luminosity, this is L equals L over 4 pi d squared. This is color. And a nearby stellar cluster, you would see it looks like this. And another cluster at distance, you see something that looks like this. All right? Now, these two are offset from each other. Suppose they're offset by a certain amount here. What does that mean, to be offset here to here? Now, this is a cluster of stars nearby. Here's a cluster of stars further away. We assume that the main sequence is exactly the same for the distant cluster as for the nearby cluster. But this is apparent luminosity here. The stars are all, suppose the stars are fainter by a factor of 4. Everything is the same here, except they're a factor of 4 times fainter. How many times further away is the cluster? 2. All right? So that right away, that tells you the relative distances of clusters. And with this mechanism, people can determine the distances inside the galaxy. They determine roughly how big things are. Okay, and they measure this out. It works to a distance of order 10 to the 5th light years, 100 kiloparsecs. All right, so that's one method. Now another method is to you want to measure distances and distances of everything. And what you can do is you look for something that you can see at great distance. Something you can see at great distance is supernova. Supernova can be seen all the way across the universe, and that's why it's so useful for standard candles. But supernovae are still rare, and you cannot use them every place. What is more common is the Cepheid variables. They are big light. They're big stars that pulsate. The bigger star pulsates, and it can be seen to quite a distance. They're supergiant stars that pulsate. Those are Cepheids. So the Cepheids can be used out to 10 to the 7th light years. That's quite a ways out. And so you use those methods. This is a method that was used by Shapley. I'm sorry, Hubble. We'll talk about that more today. All right, so measuring distances is key for astronomy. It's what astronomers do all the time. Okay, now if you go back, it's all a distance ladder. Radar imaging, stellar parallax, nearby stars. It goes as far as a cluster known as the Hyades. You use this technique to measure star luminosities of spectra, and all this goes on. And you use this technique to apply to galaxies as well as our own. And until these techniques were applied very carefully to galaxies, we realized the galaxies are not in our galaxy. The external galaxies are external. We had no idea. All these galaxies seen out in on space, as seen in the first slide today, we have no idea how far away that thing is. It could be right around the corner. How do we know it's as far away as it is? We had nothing to tell us that. In the 1920s, it was a big debate. Okay, so we use these methods, and they're very carefully calibrated one to the next. Of course, these distance ladders are only as strong as the weakest rung. I mean, it's been said, you go up a ladder, if this rung is broken, then everything beyond it is broken. You can't get there, or you're going to get there with error. You need to calibrate and understand how this works. And if you read the literature, it's all how to calibrate this stuff. Everything in the literature is trying to figure out how to measure distance when you can't go there and measure it directly. Measuring distance is a trick. It is a real trick to be able to do it at all. All right, so what makes a good standard candle? This technique is really powerful. This technique of luminosity functions, that's an excellent technique. You compare the main sequence, and you know from parallax, from the Pleiades are further away. The main sequence fitting is a very powerful technique, and astronomers use it all the time. But you have to do it. You can't use it in external galaxies because you can't see the individual stars. In external galaxies, you haven't got a prayer of seeing the sun or stars like the sun or any bright stars. You just see a smear of light. And with the smear of light, it's not going to do any good. You have to break it up into individual stars, and you can't do that with a Hubble Space Telescope or anything. The galaxy is so far away, it's all smeared out. So you need something that works to a greater distance. One of them is the Cepheid stars. All right. They're good standard candles. They follow a well-known period luminosity relationship. You can look up. The longer the period, the brighter the star is. That's all been calibrated. the very long period stars, you know, if it takes a week to blink, the star must be pretty big. If it takes only a day to blink, the star is small. And that's basically how they work. Because they're bright giants, you can see them far away. But that's not good enough either. You can't see them to the edge of the universe. You can only see them out to nearby. All right. Now, the question is, if you just see these swirls on the sky, you have no idea what's what. Let me say roughly what you see. Okay. Here's the whole sky picture, and here's a galactic plane. And there are swirls up here and down here. These swirly galaxies. But there's no swirls. There are very few swirls in here. They're only seen at the South Pole and North Pole. Why? Now, 100 years ago, people didn't have any idea of dust and extinction of light. It turns out that there's stuff in here, we don't see it easily, but there's dust up here in the sky that it scatters the light away, and you can't see through it. So we didn't know that. And so all we knew is that there are these swirly things, top and bottom. We don't know a damn thing about anything. And now the question is, what are they? What is this? We didn't know we lived in a galaxy, or the galaxy of spiral structure. So what could they be? The swirls could be stars, maybe. That was the thought. Are they extragalactic stars? Now, remember we had terrible pictures. Terrible. Not anywhere near as nice as the pictures I'm showing you. So this was an uncertain object. What was going on? And as such, there was a huge debate, a big formal debate, sort of formal, that occurred in the National Academy. And the debate was in 1920 between two experts, Shapley and Curtis. And they debated what is it? Are these extragalactic swirls? Are they indicative of star formation? Okay, and they knew nothing. Now, the question is our galaxy the one galaxy in which we live the entire universe? Or are these cosmic swirls external galaxies distributed? They go on forever. Cannot see an end to them. Which is it? Well, they didn't have any information about the swirls. Telescopes were too weak. They had photographic plates, fairly crummy. Distribution is not isotropic. Isotropic, everybody know the word isotropic? Isotropic means the same in all directions. All right, the distribution of these swirls. If the sky, if it's partly a galactic, if it's extragalactic phenomena, you would expect the sky to be the same here and here and here. You pick any random direction, the sky should be the same. Well, these swirls are not the same. They're most definitely not the same. And besides that, there are much more swirls here than here. Why is that? Well, I don't know. They didn't understand what this meant. And so it didn't fulfill the basic requirement that the distribution be isotropic. All right. Now, the reason they weren't isotropic largely was due to the dust that they didn't know about. And that's what made them look so clumped. There's so many here and here and none here. All right, are they stars in formation? Well, if you don't know anything about how stars are made, you can say, yeah, they look like stars in formation. And they didn't, that was thought to be the case. The subject was completely debated, and they wanted to make sure, they aired the points. So what do you do to try to clarify this? Well, you want to understand what it is. You might look for Cepheids in a galaxy, because Cepheids are bright enough to be seen in a galaxy external to us. You won't look for main sequences, because the main sequence will be the same, all smeared out. But a Cepheid star could be detectable, could be detected. All right, so none of this had been done. All right, except for Hubble. Here's a picture, it must have been taken in the 40s. Edwin Hubble played a large role. He discovered, in the 20s, he discovered Cepheid variables in the Andromeda galaxy. Remember, these are the light bulbs that blink on and off once every, well, in this case, he's looking for things that vary once a week. Blink on, blink off. He takes a series of plates of Andromeda, and he sees the variability of the star. And he realizes that this blinking star is a Cepheid, much like those he's seen in our own galaxy, only it's very faint. That means that Andromeda has to be external to our galaxy, is very far away. That was incredible information that was discovered by Hubble. Okay, he calculated the distance to Andromeda and found it to be 2 million light years. Remember, the distance to the center of our galaxy is 28,000 light years. All right, so the 310 to the fourth compared to 210 to the sixth. So it's 100 times further away than the center of our galaxy. That's external. That is an external object. Okay, it's not in our galaxy. That's what he concluded. Okay, and he then went on to develop classification schemes. We'll talk about that briefly. All right, he was really an important guy, and he had a space telescope named after him. All right, his greatest achievement. Of course, he was 40 years later. They named the space telescope after him. Anyhow, he did fantastic things for the field and made the subject into a modern topic today. He did it because he painstakingly measured the plates night after night after night and saw variable stars in them. And that was clearly essential. Okay, now let me turn a little bit to the interstellar medium, which is the stuff, all the junk stuff between the stars, the vacuum of space, which isn't really a perfect vacuum. Okay. All right, mostly a vacuum, not quite. The interstellar medium is mostly gas and dust, individual atoms. Large grains made of carbon and oxygen that's really just floating in space. Those grains are emitted by red giant stars as the star is getting old and tired and spewing out all this junk. All right. Now, this scatters radiation, hides the Milky Way from us, and it can be seen in the radio and infrared portion of the spectrum, and is important for the cycle of gases to and from stars, to making stars, processing the remnants of old stars. And this is the plane of the Milky Way, drawn in some, I don't know what that is. There are clouds in there, molecular clouds that contain the remnants of supernova remnants. The clouds collapse in star formation. They collapse in gigantic clouds that are beautiful, beautiful pictures taken by Hubble Space Telescope. And these clouds are gigantic mass concentrations, and new stars are made from them. The fusion, it goes on and on, cycle around. Those hot bubbles are made when the gas blows up in the stars. It cycles around and around, just like the carbon cycle you learned about in elementary school. We'll spend a long time learning about the carbon cycle, how the plant takes it up, and then it grows, and the plant dies, and then it's released, and then it goes up in the atmosphere, round and around. Well, here is the same round and round. The cycle of it's eaten by the formation of clouds and stars. Nuclear fusion makes this processes it, makes some of it into heavier elements. The star blows up, and again, it's the same process. Of course, instead of taking 5 years or so to cycle around and around, it takes here 50 million years, or 500 million years, a little longer, but it's the same idea. Okay, so there's a cycle. Heavy elements, stellar winds, mostly red giants, planetary nebula, supernova. Those are the three elements of how the interstellar medium gets material. Stars blow bubbles around them. Supernova, that was one. Here's another one. These bubbles are blown around stars. Sometimes the ejected material is supernova, is incredibly fast. It's moving 10,000 kilometers a second, just ejected out of the star. And that's much faster than other motions. And so it sweeps up material like this, excavating bubbles. It has very hot temperature, emits X-rays. It's quite, they're very, very, very energetic events. Okay, and they fill the Milky Way's disk. The whole region of us and the neighboring stars is largely filled with supernova bubbles. Huge bubbles. Even though the supernovae are not very common, they generate these bubbles that fill, say, 20% of the sky, 20% of the volume in space. Okay, so all that process makes stars. That gets incorporated into the stars that are formed. The material begins life with more heavy elements than it had before. And this supernova remnant will just blow everything out into interstellar space, except that that gas was there to intercept the blowing of the supernovae. So this is an important ingredient to the making of us. You have to have this gas in space, otherwise there's nothing to capture the heavy elements blown out by supernova, and then there's nothing to make us. So this process is essential. You need them to pack the heavy elements into the stars. Okay, so now you say, well, let's take a look at the spiral structure. All right, so to understand spiral structure, this is a beautiful example of a spiral structure. This is M51. The spiral structure shows beautiful stars. These are blue stars along here. You note the dust lanes here. To one side of those blue stars, they're not really they're not in the same position. All right? But the stars are, why are the stars on one side of these dust lanes? And so let's look at this, and I'll show you a neat okay, now, so what we've got is spirals. We've got a galaxy that's revolving around. The galaxy has stars in it, as shown by the dots. And the galaxy has mass, and the rotation curve of the galaxy, by Kepler's third law, has the material move. Now watch this little star. Watch a star come into the white. I'm sorry. These are regions that are just delineated here. They are the regions of the gas clouds. Now note that the star comes up and works its way through the gas cloud. It's actually traveling around the orbit at a faster speed than is the gas cloud, particularly out here. In here, they're really at a faster speed. Follow a star, it hits the inside of the cloud, goes through on the outside. So the gas clouds do not tell you that all the material is resident there and swirling around. It is not as though the galaxy has all the mass concentrated into these bright spirals. The bright spirals are regions of young stars. Young stars. And a star can live, say, 50 million years. I mean, a hot star, really big star, lives 50 million years. How, it takes, well, that's a really hot star is only going to live 10 million years. And it takes, the time it takes a star to orbit around the entire galaxy is a lot longer. In our case, it takes 200 million years to orbit around the whole galaxy. So if we were a hot blue star, we wouldn't make it around. If a hot blue star lives only 20 million years and the star in the orbit time is 200 million years, you're only going to make 10% of the way around. So what does that mean? What that means is that the stars, the hot blue stars, they're going to shine because they're going to shine all the time they're alive, and that time is the time when they're near a gas cloud, where they formed. The forming gas cloud is the origin of the star, is the position where the galaxy, where the stars are going to be seen. So let's go back. Okay, so the way this works is that the structure is rotating around this way. Here is the dusty region of dense stars, where the star formation is occurring. And the stars rotate out of that. So here is the direction it moved, and this is how far they can move before the blue stars die. They don't move very far while the blue stars are alive, but they make beautiful spiral patterns. So therefore, the stellar distribution is really very uniform in here, but the stellar distribution of the blue stars is not. The blue stars show where the stars are made, and they're made in a very irregular pattern, like this. Now, why does why does the gas crowd up in these sort of jams? Now, all of you have driven before, and you're all experienced drivers, and I presume, and you come into a traffic jam. What is a traffic jam? A traffic jam, it's not as though it's stopped somewhere, but it's a point of the traffic that's moving slowly. All the traffic is flowing at, say, 60 miles an hour, but this jam is a point of the traffic where it's a piece of traffic that's flowing slowly, say 30 miles an hour. And you ram into it at behind, you hit your lights, you don't hit the car in front of you, and then 5 minutes later, you take off. Why is that? What you are experiencing is one of these traffic jams. You run into something, slows down, actually makes stars right at that point. It slams and makes a compression of material. It's dense enough to make stars, and the stars are made. And then they exit on the other side, now in a bright new car, bright shiny car, after having rearranged a few of the knickknacks on the cars in the middle. That's what a traffic jam does. All right? These traffic jams in space are exactly the same as traffic jams on Earth. Do you believe it? All right? Because the traffic jam is not fixed. You say, well, this jam was caused by, how did the jam get started? Well, somebody had a flat tire, traffic slowed down for a while, and the traffic slowed down, made it such that the cars behind it hit to the traffic jam and slow down. It's a chain reaction moving backward on cars, but it's moving forward in space and where it occurs spatially. And so you can see these traffic jams, and they behave exactly the same as these traffic jams do of structure forming in galaxies. It's the same idea as the traffic jams that form. The same idea of spiral patterns forms around stars when the stars are making planets. It's very common. Okay, so it looks all right. Spiral patterns, a beautiful structure. All right, they are not fixed. This is what you have to remember. They're not fixed strings of stars. They revolve like fins. It's not right, because particularly inside the center, the rotational speed is fast, just like the inner planets rotate up fast and the outer planets rotate slowly. The same is true in a galaxy. And so it can't really be a pinwheel that's rotating around, because then you'd ask for the pinwheel to get tighter and tighter and tighter every turn. That's not right. Okay. All right, they're compression waves propagating. They're called density waves. And they orbit the galactic center, but not at the same speed as the stars themselves. Okay. All right, and they appear blue compared to the other material in the galactic plane. That's because they make new stars in that region, and the new stars do not last very long. It's really pretty incredible to see how short a time the blue stars live. Okay, let me skip this. All right, so now the halo versus the disk of material. The stars are young. Hang on a second. Okay. You ask the question, what is the elemental abundance of material in the stars? You know, we have a lot of carbon on the Earth and oxygen and stuff like that. Those are necessary for life. But not every star has to be born with the same amount of carbon and oxygen. They could vary, and we see that they do vary around the galaxy. It just varies according to the amount of heavy stars there were in its vicinity before it was born. Okay, so stars in the disk are young, but stars in the halo in the center of our galaxy are very old. So this is telling us something about the formation history of the stars, and it tells us something about the history, the cycle of histories that the galaxy went through. The galaxy is old. It's the total universe, we'll see later, is 13.7 billion years old. You may wonder how I know that, but I'll tell you why. And the galaxy was born, we think, a few billion years later. And probably some of the stars were born about the same time. So the only ones left are the very low mass stars, and they are very red. So that means they must have formed early with very few heavy elements, no interstellar medium in the halo, and they stopped formation a long time ago. Okay, now the galaxy orbits in the halo are very strange. If the whole galaxy is rotating around, the stars out of the disk are not confined to the disk, and they have orbits that go up and down. Some of the nearby stars, we know of a few stars that have a large proper motion, and they're moving out of the plane of the galaxy. They are on an orbit like this. Okay, stars in the disk orbit around in crazy directions, but stars in the halo of the galaxy don't have such characteristically refined orbits. They're not all moving in circular orbits around the galaxy. They are moving, instead, they're moving up and down. Okay. The stars in the bulge do rotate the same direction as stars in the outer disk. But this is something, this is all details of how the galaxy is put together. And they're plunging orbits of stars as they orbit around the disk and the bulge. An example of a star that orbits, that we know is orbiting like this is a nearby star known as Barnard's star that has a motion, I told you already, has a proper motion of 10 arc seconds per year. Very, very fast compared to most stars which have very small proper motions. Okay, so these are characteristics of objects in the halo of our galaxies. The mass of the galaxy is determined by Kepler's third law, the same law that we use for measuring masses of planets. Exactly the same. P squared varies as 1 over a cubed. The mass, and this is the period of the orbit, varies inversely as the cube of the mass. This A is the semi-major axis. This could be 1 AU for us, or 5 AU for Jupiter, et cetera, et cetera. Okay, so if applying this to the galaxy, the sun's distance from the center of the galaxy, 28,000 light years, 1.75 10 to the 9th astronomical units. 230 million years is our period, and that's 2.3 10 to the 8th years. You plug this into the sun's orbit, and you find that the mass, you plug in is A and the period, and you find that there's 10 to the 11th suns, 10 to the 11th times the mass of the sun, interior to our radius. You learn that right away, just from Kepler's third law. All right, the total mass of the galaxy, however, is a factor of 10 larger, at least a factor of 10 larger than what we can see interior to us. This is something we'll talk about later in the course. It's a huge effect. Total number of stars is gigantic. Here is Andromeda, M31. This is the galaxy near us. This is the one that Hubble found to be 2 million light years away. And this has, this also has about the same number of stars, about, as that in our Milky Way. Okay, now the rotation curve of the galaxy is interesting. Here's the rotation curve of the sun. The sun makes Mercury moving fast. Venus and the Earth is moving just under 30 kilometers a second. Jupiter is rotating slower, or moving slower. Uranus, Neptune, they all fall according to Kepler's third law. However, in the sun of the galaxy, it looks like this. Very different. All right? And we're going to now try to measure this quantity. Let's see. Okay, suppose we're looking at our galaxy edge-on. All right? And we just look at a galaxy, and we can measure, because we have a slit, here's a slit laid on edge of the galaxy. The slit has the capability of measuring the spectrum here, 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 here. All these points can yield spectra of the galaxy. So let's try this. Suppose I measured the spectrum right here. Did it happen? Oh, wait a minute. What's this do? How does this work? Oh, hell with it. I'll skip that for now. We'll come back to that. All right. So when you measure the rotation of the galaxy, it's very different from the rotation curve of the sun. But the rotation curve of the sun is due to Kepler's third law applied. And of course, we know our solar system is dominated by the mass in the central object. Jupiter is a very small mass compared to the sun. And so you end up with a law like this, 1 over r cubed, just like you'd expect. The galaxy, on the other hand, has mass distributed everywhere. It's not concentrated in the center. It's every place. And this is what you measure by measuring this rotation curve. So you can see that there is mass out here, different shape than that of the galaxy. And we'll talk about what this means in terms of dark matter when we go on a little bit. All right, but this is the rotation curve of the galaxy. All right, it is the mass in the solar system is all at the center. The mass of the galaxy is distributed not at the center. That's what you expect it to do. But the question is, why does the rotation curve stay high up here? Beyond our radius, we run out of mass. At least we run out of stars. As you go further out from the galaxy, the stars are fainter and fainter, and they shouldn't have any mass, and the rotation curve should have done this. But it doesn't. The rotation curve, instead of falling, stays high. What does that mean? If the mass is traced by stars, it should drop. The curve should have dropped like that of the solar system, but it doesn't. The rotation curve of the galaxy is very high, very, very high. All right, so now this is strange. So if the mass, if you plot this whole thing, what we are finding here is a hint of dark matter in our galaxy. We seem to find evidence for material that we cannot see. It's called, therefore, dark matter. And we don't know what it is. But what can we say about it? What we can say is the following. This is a common occurrence. All galaxies appear to have the same behavior as ours. A lot of mass distributed out in a halo keeps going forever and ever. All right, this is a strange, strange, strange object. The measured mass does not converge to a finite value. When you add up the mass and the outer regions, it does not, there's no way that it's going to sum to a solar mass or 10 solar masses or 10 to 12 solar masses. It seems to grow and grow and grow. We're assuming that Newtonian mechanics still works. It must still work out there, we think. Although people have said, well, let's make substitutions and see if we can change it. And we can't. All right. Appears to be, you cannot measure the total mass of the galaxy. And apparently, the mass of the galaxy is dominated by this dark matter. We'll talk more about this. All right, so we'll talk about that as we go on, and that'll be on Tuesday. First of all, I want to talk a bit about something that Hubble found. He found these galaxies. They're called ellipticals and spirals, and then something in between he called lenticulars. He published in 24 very faint Cepheids of M31. That's the nearby Andromeda galaxy. All right, and he saw them to be external galaxies. So then after he proved that the galaxies were external, he then studied them in detail. He saw lots and lots of galaxies on plates, and the galaxies were either ellipticals or spirals, like us. The spirals were different types. They had bars like this. He called those bar spirals, SB, or they didn't have bars like this. All right, SC, etc. It's not important to know what they are, but he classified them. All right, the classification was 3 types. There are 3 types of galaxies. There's a spiral galaxy, like us. There are elliptical galaxies. And then there's a type called a lenticular galaxy. Irregular galaxies. And they're very common. They're not the big ones, but they are common. And these galaxies span a gigantic range. They're from dwarf galaxies. A dwarf galaxy might contain 100 million stars. That's it. All the way up to giant galaxies. Giant galaxies could contain 10 to the 12 stars, 1 trillion stars. A huge range of, a factor of 10 to the 4th between giant galaxies and dwarf galaxies. Galaxies don't have a definite size, like a solar mass. They have a huge range of sizes. All right, so we'll talk about how we understand this in the coming weeks. But here are some more pictures. Galaxies, this might look like us. Disk component, spheroid and bulge. Here are bulges, dust lanes all around, relative size, et cetera, et cetera. And these are seen around the sky. Okay, now let me show you just quickly. Okay, here's a galaxy near us. I should turn these lights off so you can see this better. This is a galaxy known as M82. These are, of course, recent pictures, a lot better than Hubble could have taken. Okay, this is a picture that is a combination of optical and the emission lines are seen. This is a line of H. This is a line, I believe the red is a line of H alpha. That's hydrogen Balmer excitation line. All right, here's what it looks like in visible. If you look at it in the X-ray, just in the center, what is showing is that it shows the central active galactic nucleus, which is very prominent on this galaxy. All right. This is what it looks like overall from photographic plate. And this is a beautiful picture showing the gas flowing out from the central nucleus. This galaxy is really blowing up, as much like our own galaxy, we think. All right, so this is a pretty incredible object. In the radio, you don't see very much. Infrared, you don't see much either, etc. Near infrared, beautiful. Shows you the plane, all right? So absolutely gorgeous pictures. And this one is showing all the activity of the galaxy, the nuclear activity of the galaxy. That's a star-bursting galaxy. All right, here is another galaxy, a very pretty galaxy, M81. No, the other was M82, I'm sorry. This was M81. All right, here's a picture. Here, let's take X-rays first of all. In X-rays, you can see a very strong nuclear emission. This is an active galactic nucleus that's shining at you, very powerful, obviously. A little bit of activity on the outer regions here. Ultraviolet, visible. All right, near infrared. Further infrared. All right, so these galaxies are showing the younger stars on the different portions out here. The mid-infrared is showing the dusty regions and the nuclear region as well. Okay, so this is the prettiest. All right, so that is the view of a couple galaxies close up. Of course, Hubble would have loved to see any of these, but he obviously lived too early to see anything. All right, so these galaxies have surprises in them, and it's beautiful to look at these different things. Spiral galaxies we have barred spirals, all right? And this apparently is a situation for us. We are in a barred spiral because we can tell by the anisotropy of the matter. And sometimes a galaxy will look like this. This is an elliptical galaxy with these rings of material it's absorbing. All right. These different galaxies are seen all over the sky. Everywhere you look, there are different types of galaxies. Here's an elliptical galaxy. Elliptical galaxy is just what it says. It's elliptical, spheroidal. It has no disk component, very little interstellar medium. It appears red in mostly old stars. Here's a giant elliptical. Here's a dwarf elliptical. The dwarf elliptical is so close to us that we can see the individual stars. This one's further away. We can't see the individual stars. But you can see these tiny little, the bright spots are globular clusters of that elliptical galaxy. This elliptical has thousands and thousands of globular clusters. We only have 100 around our galaxy. But there are, I think, 10,000 galaxies around this elliptical, which is known as M81, I think, or whatever. All right, so what do these things mean? Why are they different? All right, and furthermore, they're clustered in groups and clusters. Most of the time, most of the galaxies are found in groups. There tend to be spirals, where our local group, our assemblage of us and M31 is known as the local group of galaxies. That is, everything out to 2 million light years is our local group. You didn't know that's your neighborhood, did you? I'm just going to the neighbor to get some milk for this recipe. I'll be back later. 2 million light years away is a little bit longer time to get there. All right, and so galaxies are in clusters like this, or sometimes in really, really big clusters. That is a rich cluster of galaxies. All right, so hundreds of objects there. So we want to understand why, and that'll be it. All right, so next time we'll talk about all this stuff and what it means, and we'll take it from there.